Okay, here we are. Thermodynamic probability, like I said, module 2.2. We're going to look at thermodynamic probability, the most probable configuration, and we'll conclude. Now, in an isolated fluid, the energy and the total number of particles are both constant. Interactions between the particles of an isolated closed system will result in changes in the numbers of particles occupying the energy state. If the particles are distinguishable, will result in changes in energy state of each particle. These interactions might be collisions of the molecules of the gas themselves, or with the walls of the container, or energy interchange between oscillating molecules in a crystal. So we're looking at either a gas or a solid. Now, every such interchange results in change in the microstate of the ensemble, but every possible microstate must satisfy the conditions of constant N and E. We'll also still see that in the Boltzmann statistics. The number of equally probable microstates that correspond to given micro is called thermodynamic probability, W. So, assuming there are N atoms, and we have N1 atoms in state 1, N2 in state 2, N3 in state 3, and so on up to state N. Now, this is the equation we use for W. W is equal to capital N factorial divided by N1 factorial, N2 factorial, up to Nn factorial, where small n is the total number of states that we have. Now, we want to use this to show that last illustration we did in module 2.1. For 300 configuration, W will be equal to total n is 3. So 3 factorial, the first energy 3 is only one atom that took the 3, that is 1 factorial. Then 2 atoms took that, that's 2 factorial. And if you divide that, it gives us 3. For 210, the 3 is still there, 3 factorial, total number of atoms. Then 1 atom took 2 oranges. 1 atom took 1 orange, and the other atom has no orange, that's 0. So that is why you have 1, 1, 1, and it gave us 6. Then for the 1, 1, 1 configuration, we have 3 factorial over 3 because all the 3 atoms took 1 energy level, that is 1, 1, 1, and that is giving us 1. So if you remember, in module 2.1, we also got 3 plus 6 plus 1, which is equal to 10. So we have solved this using the thermodynamic probability instead of using the diagram of the boxes. Now we go further to increase. We now use this formula for 5 quanta distributed, 5 loosely coupled atoms. Look at it. The first will be 5, 0, 0, 0, 0. So one person takes 5, the rest is left with 0. One person takes 4, the left is left 1, and the rest 0. 3, 2, 0, 0. 3, 1, 1, 1. 2, 2, 1. 2, 1, 1, 1, and then 1, 1, 1. Each time, the total of this must be 5. This is 5. 4 plus 1 is 5. 3 plus 2 is 5. 3 plus 1, 1 is 5. 2 plus 2 plus 1 is 5. 2 plus 1 plus 1 plus 1 is 5. And of course, 1, 1, 1, 1 is 5. So now, we want to calculate the microstates. For the first one, W will be 5 factorial, 1 factorial, 4 factorial. Gives us 5. For the second one, 1 factorial, 1 factorial, 3 factorial. So doing the same thing to all of them up to the 7th one, we will have 5 plus 20 plus 30 plus 30 plus 20 plus 1, which will give us a total of 126 microstates. We went ahead again, look at that, 5 quanta distributed among 10 atoms. Remember the last one gave us 126. We have now increased. It's still giving us the same thing, except that we have brought in another addition of 5 atoms that all of them will now have 0, 0, 0, 0. Look at it from here, from the column 1, 2, 3, 4, 5, 6, the 7th column. All of them will be 0, 0. But it's still part of the calculation. So we'll do the same thing, 10 factorial. Now it is total number of atoms is 10. The other one was 5. 1 factorial, 9 factorial, 10. Now look at that. We'll calculate as 10, 90, 90, 360, 360, 480, 252, and total is 2002. Now when you carefully look at this, you see that there's one particular configuration that is having 840. You see, this configuration has 840, whereas the closest one is 360, 360. So one particular configuration is standing out. So as the thing is increasing, one particular configuration stands out, as we'll shortly see. And that is what we call the most probable configuration. So in the last computation we did, that one with 840 can be described as the most probable configuration. Look at it. So that as the total number of possible microstates of an assembly or thermodynamic probability of assembly is summed over microstate, the thermodynamic of each microstate. As the number of quanta and number of oscillators increase, as it increases, then it becomes phenomenally large. Thus, for 1,000 quanta and 1,000 oscillators, you can imagine if we tell you to do this assignment now, it becomes a problem. The number of microstates is 10 to the power 600. I'm not sure whether your calculator can even carry this. Now, as the number of quanta and oscillator increases, a large proportion of micro begin to accrue to a particular one of the available configuration. And this configuration is called the most probable configuration. Now, I want you to do something where you go back. For us to check this most probable configuration, we take a die. The first we did here is to toss the die 2 times. Look at what we have. 1, 2, 2, 1, which gives us a total of 6. Now when we toss the die 4 times, it now increases. Now I want you to go back, bring your pen and paper, toss the die 8 times, 12 times, and possibly 16 times. And then let's see what you will get. And then from there, see if you can see any particular configuration standing out to become the most probable configuration. We've come to the conclusion of this module. We have thermodynamic probability we've looked at. We look at the most probable configuration, and we also looked at illustrations. I hope to see you in the next class. Thank you very much, and God bless you.